Good morning, good evening, good afternoon, wherever you may be watching this around the world, whether you're joining me live or whether you're watching the recording later in the day. And welcome to the final episode in the series of 4 Christmas lectures, where I've been looking at the correspondences between the 7 Hermetic laws in the Kybalion and electronics, particularly radio frequency electronics. And I put up a little bit of a puzzle later on yesterday by putting up this diagram here and said, what might that represent? I think it was Claire Miller that got the closest answer. What that could correspond to or represent is if we were to look at the human body and the human energy system, particularly, and we were to draw a circuit diagram for it, then it would look something like that, in that there are 7 tuned circuits, and they would represent the 7 chakras, and they take the energy from above down into the earth and vice versa. It's very well known now that the body actually has an electromagnetic field. We give off electromagnetic waves, and we also receive electromagnetic waves, and this is how we would do it, with each of these tuned circuits being tuned to a different frequency. Lowest frequency down here, highest frequency up here. Yeah. So in a way, what we've got is in the human energy system is like a transformer, but not like a transformer that we talked about a couple of days ago, but more what this does is it transforms frequency rather than voltage. And what we can do is we can bring high level frequency up here, put it down here, and lower the frequency of it, or we can take lower frequency from down here and bring it up here and increase the frequency of it. So that was my little puzzle. So well done, Claire. I think you were the person who got the puzzle the closest. And what we talked about yesterday was about antennas. So I want to talk about antennas today, because they're the final piece in the puzzle, really, as far as what we've been talking about with the correspondence. So what we do is we would put an antenna on either a transmitter or a receiver. So the antenna on a transmitter enables us to put the wave energy or wave power out into the ether. And we put an antenna on a receiver to draw the wave energy or wave power out of the ether. Yeah. So the simplest antenna is what's called a dipole. A dipole is essentially 2 pieces of wire like that. And what you would do is the length of that wire is important, because what we want is, ideally, we would want the length of that wire to be the wavelength of the frequency that we want to pick up. So we've talked about Radio 2 on 200 kilohertz, which used to be broadcast from Droitwich. And at 200 kilohertz, a full wavelength was 1.5 kilometers. So a full wave dipole for 200 kilohertz would be 1.5 kilometers long. Yeah, 0.75 on each end, feeding that into the receiver. But obviously, for most of us, having an antenna 1.5 kilometers long would be a little bit difficult. So the transmitting antenna at Droitwich, you used to be able to see that when you drove past on the M1, was a very, very, very big antenna. But then what we can do is we can receive that from antennas which are smaller, but what you do is you make it half, quarter, eighth, 16th wavelength. Yeah, that's the most simple antenna. But then the thing that we want to start looking at with antennas is a thing called gain. How do we actually get gain from an antenna? Which means gain is it's almost like the antenna is like a magnifier. It's like an amplifier. And gain is measured in decibels. And 3 decibels 3 decibels gain is multiplied by 2. So if you've got an antenna that actually had 3 decibels gain, you'd effectively give out twice as much power and energy as you were actually putting into the antenna. And also, if you were receiving the antenna, what you do is you'd be doubling, or you'd be able to pick up signals which were half the amplitude, if you like, of a regular dipole. So this is how we can actually get gain on the transmitter and gain on the receiver. Where this is important is, for instance, with the foundation license for radio amateurs in the UK, you're limited to 10 watts, which isn't a lot of power. But if then we can build antennas which boost that power, because antennas have what's called ERP, which means effective radiating power. So what that means is, for instance, if we had an antenna which had got 3 decibels gain, and we put 10 watts into that, the effective radiating power would actually be 20 watts. Yeah. So, a lot of research has been done into antennas by radio amateurs because they had limited amounts of power that they could use. Like literally the Radio 2 transmitter was putting out kilowatts of energy, of power at 200 kilohertz. Yeah. Whereas we're limited to watts as a radio amateur. So a lot of radio amateurs did a lot of research into how do we get gain from an antenna. And you'll have seen some of these antennas we don't see them that much these days, but you used to see them on every single house's chimney in the TV antennas. Yep. So if we took what's called a Yagi antenna, so again, we've got our dipole. Yep. But then we put behind that another either piece of wire or another piece of metal tubing. This is called the reflector. And then we put another piece of wire, another piece of tubing in front of it. This is called the director. Then that kind of construction of an antenna will actually give us approximately 9 decibels of gain, which is doubling 3 times. Yep. So it's 2 times 2 times 2. Yeah. So that's 2 times 2 is 4 times 2 is 8. So essentially, if we put 10 watts into there, then the effective radiating power becomes 80 watts. Yeah. Now, or it means, if we use that as a receiver, it means we will be able to pick up signals which were 1/8 of the power of what you'd be able to pick up with a straight dipole. So that's how these things work, and how we can get more power out of certain antennas. Now, interestingly, as I said, to create an antenna, full wave antenna for Radio 2 at 200 kilohertz, that would be 1.5 meters long. If we were looking at 30 megahertz, then that antenna then becomes 10 meters. But as we're now starting to look at millimeter waves or microwaves, then a dipole at, let's say, 60 gigahertz is only 5 millimeters long. It's tiny, which is how they can fit these antenna. They could even fit something like that as a microwave antenna onto a circuit board in your mobile phone. So they got the gain from when you're transmitting with your mobile phone and the gain when you're receiving from your mobile phone. Now, even more that we can start to look at now with this increase in frequency is what's called phased arrays. Now, phased arrays is where you have a whole series of aerials, which you add the signal that comes from them. Now, phased arrays can do a number of very clever things. One is they have very high gain, like as much as 18 decibels gain, which is 2 times 2, 4, times 2, 8, times 2, 16, times 2, 32, times 2, 64. So for instance, if we put in 10 watts into a phased array, it would be the equivalent of 640 watts effective radiating power. And probably the biggest phased array that you'll ever come across, if you go onto Google and search for something called HAARP, HAARP, then that's the phased array that was built by the US Navy, actually, I think, in Alaska, that enabled them to radiate megawatts of effective radiating power at shortwave length. And the other thing that this does is not only very high gain, but very directional. If any of you've got a sound bar, on your TV, and the sound bar's got lots of little speakers in it, and it's actually a phased array, because phased arrays work with sound as much as with radio frequencies. And even though the speakers are staying in one place, with a sound bar is actually able to put the sound in different parts of your room. So with a phased array, they're physically fixed, but you can they create quite a narrow beam, and you can point that beam around in any particular direction, and enables you to get more effective radiating power. Now, that's important with these kind of microwave frequencies, because microwave frequencies have an impact on molecules. If we were to go through different frequencies in the microwave band, then what happens is certain molecules absorb certain microwave frequencies. Now, effective radiating power, 640 watts, that's energy. It's impossible to create energy, and it's impossible to destroy energy. All that you can do with energy is to transform it. So what they noticed was at a frequency which was 2.45 gigahertz, suddenly that frequency was absorbed. And that energy at 2.5 gigahertz was absorbed by water molecules. And what it caused was the water molecules to vibrate really, really fast, and it caused them to heat up. That's why 2.45 gigahertz is the frequency that we use in microwave ovens. Because what the microwave does, what the 2.45 gigahertz does, is it makes the water molecules in your food vibrate faster, and the energy in the 2.5 gigahertz wave is converted into heat, which is how your food gets hot. Then there's another challenge which has come into this kind of thing, because there's a similar absorption at 60 gigahertz, where that energy is absorbed. And at 60 gigahertz, that energy is absorbed by oxygen molecules, O2 molecules. And again, it causes them to vibrate, and it causes them to split into monatomic oxygen, which is just an O rather than an O2. But oxygen, just a monatomic oxygen, wants to bond with something else. So it bonds with other O2 molecules and becomes O3 and becomes ozone, which is why at these kind of frequencies, 60 gigahertz, the distance that those waves can travel through the air is limited, which is an RF engineering challenge that people are facing as we as we move into higher and higher frequencies, which, as we talked about yesterday, is what we need to do to be able to increase the data rate of the information that we can put into the wave. So that's really finished off the whole thing. That you've got a radio frequency engineering 101 in just 4 lectures. Thank you for joining me for these. I've really enjoyed sharing them with you, and I've loved the feedback that you've been coming back with. And please, if you've got any questions, now we've done all 4. If you've got any outstanding questions as a result of watching these, then just put them into the comments thread. And if there's enough of them, then I might do another lecture in the new year to answer those, or I'll just put if the questions are really simple to answer, I'll just put them in the thread. So I wanted to bring in again my friend Dr. Simon Fricker to enable us to send 2020 out with a bang, because I think a lot of you want to do that. So here's another demonstration that he did. This is a demonstration of a rocket engine. And this particular reaction that Simon's going to talk about actually was the discovery that enabled us to leave the Earth's atmosphere and send rockets to the moon or launch satellites into the air and all those kind of things. So let's go over to Simon for this Big Bang Sending Out 2020 demonstration. Wow. Thank you, Simon. That is absolutely brilliant. I think that's really sent out 2020 with a bang. And I'd like to wish you all a very, very happy new year. And as I've said over and over again, let's focus on making 2021 our best year yet. See you in the new year.